for this part a little bit. Yeah. Now our goal, reduce the number of multiplications to evaluate this polynomial. At this point, it's not easy to find a way to do the reduction. Yeah. So we take this strategy, study a simpler case. Yeah. The simpler case, we look at the smallest problem size n equals 2. We do not choose n equals 1 because although n equals 1, it's simpler, but it's not quite meaningful, right? It's not quite meaningful. We cannot see the main property when n equals 1. Yeah, for that reason, we have to choose the smallest meaningful size. Yeah, here. Yeah. So for this step, when we choose the small problem sizes, here I talk about a concept called a problem size. Later, I will explain this problem size, this concept, right? Yeah. Later, I will, spend a little more time to explain this concept. Here, you can understand this polynomial degree. Yeah. In this particular problem, the polynomial degree responds to our problem size. Yeah. All right. And here, when we choose the smallest meaningful size. Yeah. Yeah. For that reason, we do not choose n equals 1 because it's not meaningful. All right. What do you mean meaningful here, right? Yeah, because we cannot see the main property in it. Yeah. What's the main property? You may ask me that. Yeah. Later you will see. Yeah, later you will see what's the main property there. All right. So that's one thing. The second thing, look at the annotation I made last time. Change the order of operations. Yeah. So what direction to go? How do we do the reduction? The direction, we need to complete this task. This is the direction, all right? This is the direction, yeah. Because if we look at how do we evaluate this polynomial applying additions and multiplications, we have many different ways. First, definitely it's not a unique way, right? Yeah. The way to do the polynomial evaluation is not unique. If it is not unique, that means we have some freedom to choose the order of the operations. Okay, yeah. If we have this freedom, then we have a chance to find a better solution. So we will take advantage of this freedom to explore some smart way to do the evaluation. Yeah, so that's the direction. We need to take. Yeah. All right, so let's continue. Yeah. Let's work on this polynomial first. This quadratic polynomial first. It's simple. So we're not scared by this polynomial, right? If I give you a polynomial with degree 200, then you will be scared, right? But here, degree 2, so nobody gets scared. Yeah. All right, so let's do it. First, let us do observation. What is the main property here? Yeah. Now we need to explore. We need to find the main property in this polynomial. Yeah. Okay. Yeah. Look at the brace that covers two terms of this polynomial. Can you see some special property here? Yeah. Let me open my chat area. So if you have anything you like to input, so you can type in the chat area. Yeah. All right. Yeah. The main property. Can you see there is some common factor between these two terms? Common factor. Common factor property. That's the property I'm talking about, right? Common factor property. All right, yeah, common factor x. Yeah. Then if we go back to n equals 1, yeah, here, because why, here I can explain why n equals 1, it's not meaningful. Okay, you know, based on our, our situation, not meaningful, because you will see this common factor property, this property missing, right? So that's why it's a not good case to get us started. Yeah. Now, when we consider n equals 2, this common factor property is there. Okay, yeah, so we can work on that. When we have a common factor, what technique we can apply to arrange this polynomial in a different form? When the form is different, the evaluation order could be different. All right, yeah, so because we can do the factorization, right? Yeah, we can do the polynomial factorization. That's the technique I'm talking about, factorization, all right? Yeah. So the factorization is like this. We factor that x out, then parenthesis a1 plus a2x. That's the form change. Okay, you can see the left-hand side and right-hand side, they have the same value, but in different forms. Okay? Different forms, different structures will give us different evaluation order. Yeah. So think about this structure change result in different evaluation order. Okay, this different evaluation order could give us different number of multiplications. Okay, yeah, so let us do the counting here. All right, for the left-hand side, how many number of multiplications? The first term, 1, yeah, we counted last time. Second term, 2. 1 plus 2, we have 3 multiplications. Now let us look at the right-hand side. And let's count the number of multiplications. Only 2. Yeah, only 2. Why 2? Look at 1 multiplication here, x times the parenthesis. Okay, the parenthesis is a number. To find the value of that parenthesis number, we only need to do another multiplication between a2 and x. Okay, yeah. So the total 1 plus 1 equals 2. 1 here, 1 here, 1 plus 1 equals 2. Okay? Yeah. That's the reduction, right? The number is reduced from 3 to 2. Yeah. So let's look at this conclusion. Yeah, that reduction. Okay, all right. When we apply the factorization technique, yeah, we can have this result. The number of multiplication is reduced from 3 to 2. Is that reduction significant? Yeah, look at that. Yeah, here you can see, yeah, from 3, you can see we get about 33% reduction, right? 33% reduction. That's quite significant. Yeah, yes. So we like it. All right. So this method works well. All right. Yeah. So the next question is, can we generalize this idea to the general n? Yeah. But here n only equals 2. Yeah. So our goal, we need to do this kind of improvement for the general n. Yeah. So our next step, we need to answer this question. Okay, all right. So let's move to next step. Yeah. Next step, yeah. After we try n equals 2, we get something very promising, right? Very promising. But in order to find a, apply that method to the general n, we feel we need to get a little more experience. So to get a little more experience, let us try n equals 3 case. Okay, yeah, try to consolidate our finding. All right, yeah, n equals 3. Yeah, so let's try another time. P3, this time we have a cubic polynomial. Okay, from quadratic to cubic polynomial. Okay, yeah. This time, let us try to take advantage of that freedom, common factor property, and do factorization. But when we do factorization this time, we take this strategy, small strategy here, okay? Should cover as many terms as possible. All right, so what do you mean as many terms as possible? First, we know there is no common factor for all the terms, right? So we have to reduce the number of terms. Yeah. We just skip the first term, constant term, A0. Then you can see for these 3 terms, there is a common factor x. So we just take factorization in this way. Yeah, straightforward factorization, similar to what we did for n equals 2. Yeah, all right. After that, look at the polynomial inside the parenthesis. So inside parenthesis, it's a quadratic polynomial, right? Quadratic polynomial. And we just did factorization on the quadratic polynomial for n equals 2. Can we do it again here for this parenthesis part another time? Factorization, yes. So we can do it another time. So then you can see we do factorization twice. After we do factorization twice, we get a new form of this quadratic or not quadratic, cubic polynomial evaluation order. Yeah. With this new structure, we have the new polynomial evaluation order. Okay. Yeah. Do you want to count the number of multiplications we need here? That's pretty easy. Yeah. Number one, x times the first parenthesis. Number two, x times the second parenthesis. Yeah. Number three, x3 and xx. Yeah. So the total, we have number of multiplication we need equals 3. If we go back to this original form using the old way, we need number of multiplication 1 plus 2 plus 3, right? Yeah. 1 here, 2 here, 3 here. Okay. So we get 6. So the reduction is from 6 to 3. Yeah. This time 50% reduction, right? Yeah. Quadratic case, 33% reduction. And here, 50% reduction, even more than 33% reduction. Look at that. When we increase the problem size, the reduction percentage grows. Okay? Yeah. So you can imagine when n becomes larger and larger, the reduction percentage should be larger and larger, right? The larger, the better for us, right? Yeah. Larger means we do improvement more and more. Okay? Yeah. So now it's time to push this idea to the general case. Okay? Yeah. Look at this idea. Push this method to the general case, general n. Okay? Yeah. So we do not need to try n equals 4, 5, not necessary. Okay? We feel we have plenty of experience here, so we are ready to push this idea to the general case. Now, so let's do the work here. Okay, yeah. Strategy for the general case. Now, another strategy. So here you can see for each step, when we work on a new subproblem, we may need to use some new strategy. Okay? Just like a typical football game, every time when you make some new offense, right? New offense, you may need to apply different strategies. Yeah. Here, we need to apply different strategies. Yeah. So let's look at our new strategy for generalization. Yeah. This time, the strategy becomes do factorization as much as we can. We know the key of the success in our previous 2 experiments because of the factorization technique. Okay, yeah. So since it is, so effective there, yeah, let us apply it as much as we can. Yeah. Here, this part, as much as we can, yeah, this idea, yeah. Very simple, right? Yeah. Very simple, but there is some interesting idea associated with this phrase. So what's that? The greedy idea. The greedy idea. Okay, as much as we can. Okay. So let us bring some real world experience here. Yeah, in a real world experience. Yeah. So when people try to, grab as much as they can on money, yeah. So we may say, greedy, right? But here we borrow that meaning a little bit. But here it's not a negative thing. Yeah. Although we use this word, That's quite negative. Yeah. But here, it's not negative. Yeah. We want to express this meaning as much as we can. This greedy idea. So there is a very important type of algorithms. It's called greedy algorithms. Greedy algorithms. Here, let me give you a brief introduction on the greedy algorithms. Yeah. Actually, this is a topic in our later chapters in our textbook. Later chapters, they're very late. Okay. Yeah. But in this class, we may not have enough time to cover later chapters, some materials in the later chapters. So here I talk about that. This idea is very important, very useful in our computing problem solving. So what's the description of the greedy algorithms? Apply some property. Here at the property, we mean factorization property. Yeah. Right? Apply some property as much as we can at each step. At each step, step by step. Yeah. Each step, you can take this greedy idea or greedy approach. Yeah. So that's the greedy algorithms. Yeah. Here we need that. Here we need to do the factorization as much as we can at each step. Okay? Yeah. We need many steps. Each step, we do one factorization. Then the next step, another factorization. But at each factorization, we want to cover as many terms as possible. That's what I mean, the greedy strategy. How we apply the greedy strategy here. Okay, so let's apply it. Yeah. Given a general polynomial. Okay, and when we do that factorization, we take the pattern we already have in our previous experiment for cubic polynomial. Okay, so this structure, yeah. So we get a point. Yeah. Yeah. So we can do the analogy. We try to do the same thing for the general polynomial. Okay. Yeah. So the general factorization step by step. Okay. Yeah. One step here, another step, all right, and until we get to the end. You can see for each step, we only need to do one multiplication. Okay, each step, we only need to do one multiplication till the last one. The number of multiplication we need, you can see only n multiplications. How about that? N multiplications. That's the end, right? That's the end of the evaluation. How good it is. Okay? Yeah. So that's the new solution. New solution that comes from different polynomial evaluation order. Okay? Yeah. So you can see this smart method is called Horner's rule. Horner's rule. Okay? Yeah. In polynomial evaluation. Okay? Yeah. All right. Yeah. So here, yeah, before we look at how good is this new method, let me do some summary on this greedy algorithm. Summary. Okay, yeah. So this method works quite well, greedy algorithm, right? Or greedy idea, greedy approach. It works quite well here. Okay, yeah. Yeah, when we use this thinking, yeah, here we use this thinking. That's very effective here. Okay, yeah. But here, I like to point out something important regarding the greedy algorithms. First, at each step, now, how do we look at this at each step? Okay, yeah. So this each step, we understand it with a local view. Local view. Yeah. Each step, yeah. Because to solve a problem, we need a sequence of steps, right? Yeah. A sequence of steps. Okay. That sequence could be long. Yeah. That sequence could be long, quite long. Yeah. But here we only look at one of the steps, only one step in that long sequence. So we treat it, it's a local view, right? Yeah. So it's local view, that means it's not a global view. Global view. Okay. Local view, not a global view. Okay. Yeah. So here you can see the greedy strategy. We take a local view instead of a global view. All right. Yeah. Why this way? Right? Why you take local view? You do not take a global view because easier, right? So I do not write a lot of work because the local view is easier than the global view. The global view is very hard. How can you apply some property in a global way? So here, the global way, you need to make sure you can do the best you can globally, right? Globally, you need to consider all places, covering all steps. That's too hard, okay? The global way, too hard, but local way, much easier. We do not need to look at other steps. We only need to look at the current step. The best we can do in the current step. That's much easier, right? Yeah, yeah. But the consequence you may have, the consequence we may not get the best solution. Okay, the local view may not give you the best solution. Okay, yeah. So only when you are lucky, you can get a best solution. Yeah. But it's very normal if you do not get the best solution because of this local view. Okay, so that's the summary for the greedy algorithms. Although you can try, but after you find a solution, you need to be aware of your solution may not be the best solution. Okay, you need to, have that point in your mind. Okay, you may not get the best solution. Yeah. Yeah. All right, yeah, all right. So let's stop right here for the greedy algorithms. Later, when we need to apply it another time, we will continue the discussion on the greedy algorithms. Yeah. Now we get a new solution, and this new solution, yeah. Look at the, before we do the reduction, yeah, the number of multiplications we need is this number, all right? The reduction is so big, okay? Yeah. So the next thing we need to look at, how big is the reduction? How big is the improvement in our algorithms? Okay, yeah. So the next part. Yeah. For that discussion, yeah, I want to show you the point, the impact of this multiplication reduction. Okay, yeah. From the formula, you see this is the reduction, but the formula, you may not get some big impact, right? Yeah. In your mind, do you have an idea how big is this reduction? Right? Other than the forms, they have different forms. Yeah. From quadratic to linear. Yeah. The left-hand side, that's a quadratic form. Okay. Right-hand side, it's a linear form. Linear. Yeah. Yeah. But it's hard to imagine how big is the difference. Yeah. Here, I want to visualize the difference. Okay. How do we visualize the improvement? Give you some strong impression in your mind. So that's the visualization. Okay. All right. So let's do some experiments. Okay. Yeah. First experiment. Let us consider the polynomial degree n equals 1,000. Yeah. So that's pretty big, right? 1,000. Yeah. We compare these two formulas. Before reduction, after reduction. We just plug in that number, do the comparison. Yeah. 1,000 for n and approximately 500,000 for that quadratic formula. That difference. Now you get some idea, right? 500,000 versus 1,000. That looks a little better, right? For the difference part. The difference is pretty big, at least we can say that. Yeah. Here you can see the ratio. The ratio, 500 to 1 ratio. Is that good? You only need 1/500th of the operation numbers or response time, approximately response time. Your new response time is approximately 1/500,000th of the old response time. Is that big? Think about that. Is that really pleasant, right? Yeah. Let's do another experiment. This time we increase the polynomial degree number to 1 million. N equals 1 million. Okay, yeah. The ratio should be much more than 500. Yeah, so let's look at how much it is. Yeah. Just plug in this n number, 1 million for the n side. Look at this number. How big it is. Okay. So many zeros. How do we call it? 500 billion, right? 500 billion. 9 zeros corresponds to billion, right? 500 billions, that number. Then let's take the ratio 500,000 to 1, that ratio. Think about that big difference. Okay, yeah. From the number, you can see the huge difference already, right? Yeah. Here, I like to push this visualization another step further. Yeah, because we need to associate this number to our real world experience. Then you can get a much bigger impression here. Yeah. So let me do it in this way. Yeah. I just want to show you how big is this 500,000 to 1 ratio. Yeah. Let us compare. We evaluate a polynomial with this big degree, 1 million degree, yeah, in 2 different algorithms for the evaluation. Yeah. The first algorithm, we use the, old way. Second, use Horner's rule. Yeah. And we know the result, 500,000 to 1 ratio. Yeah. That one, I like to use a convenient time unit, second. Yeah, this second time unit in second. That one corresponds to 1 second. How about that? For convenience, okay, 1 second. That means when we use our computer to do that evaluation, we need 1 second by Horner's rule to complete that 1 million degree polynomial evaluation. All right, yeah. Then go back to the old way. This time we need to use 100 billion seconds. How big is that? 1 second versus, yeah. Sorry, not 100 billion. 100 billion, so that's the number of multiplications. But we know the computer can do multiplications extremely fast, right? Yes. So 100 billion multiplications, the computer can do much faster. And here, based on our assumption, that is, we need to use 500,000 seconds. How long is that? 500,000 seconds. How long is that? Okay, let's convert to the number of days so we can see this period better. How long is it? Yeah, approximately 5.8 days. Think about that, 5.8 days. Yeah. To evaluate the same polynomial, 1 million degree polynomial, by Horner's rule, we only need 1 second. By the old way that everybody is familiar with, we need nearly 6 days, slightly less than 6 days. Think about that. That difference is huge, right? Think about that, okay? Yeah, because here I like you to do comparison. You have 2 different solutions, okay? Just doing the same thing, you have 2 different solutions. One, after you hit the enter key, after 1 second, you get the correct answer. But the one that is not very good, the better one, after you hit the enter key, you need to wait approximately 5.8 days to get a correct answer. Now you get an idea. How big is the impact of a good algorithm? Okay, yeah. So the reason I give you this first computing problem in our first module, I want to give you the impact of different algorithms and to show you the power of algorithms, power of the good algorithms. Okay, so later you should understand, after this class, we try to find the best algorithms for a given computing problem, because we know the difference is huge. If you can get a, not necessarily optimal, we will talk about optimal algorithms in our next part D. Not necessarily optimal, but we want to get the best solutions we can find. Here is a good example for that importance. The time we spend, the investment we make, definitely it's worth the effort. All right, all right, so let me stop this topic, okay, our part B. So I already spent too much time here, for this polynomial evaluation topic. Because later, next week, I need to give you our first programming assignment for this problem. So that's another reason I spend a lot of time for this computing problem. Okay, all right, let us move to the next topic, part C of module 1. If you have any question, you just type in the chat area. I need to switch to different PowerPoint slide file. All right, part C now. All right, so the title, Role of Data Structures in Algorithms. So we consider another important topic here, data structure. All right, so C.1, search unordered arrays. That's a simple problem, simple computing problem. But we can look at the importance of the data structure role. All right, our problem number 2, search an unordered array. Given an unordered array, here we use this representation with indices from 0 through n-1. Here you can see there are n elements in this array, n elements. And if we use the problem size concept, problem size in this array, number of elements, that's n size. All right, and a search key k. Given, the question, find an index I such that k equals a of I. That's the search problem. Simple search problem. It's very easy. Everyone can solve it quickly. I believe you can already find the solution quickly. But here, I like to do some discussion. So we try to learn some basic concepts in this simple example. All right. The problem type here, there are some basic problem types in this class. And this one corresponds to one of the basic problem types. That's the search problem. Search problem, all right? And the data structure is array here. All right, And the reference for this material, section 2.1. All right, here, we want to look at this question. Why the data structures are important in algorithm design? Here, we use probably the simplest data structure array. Yeah. Later, we will learn some advanced data structures. Yeah. So at the beginning, so let us just look at the simple data structures. Yeah. All right. Here, the reason. Yeah. What's the reason to use some special data structures? Yeah. So here, the typical reason is this. Through data structures, we can make our data well organized. Yeah. Usually, the data is given in random order. Okay? No specific order. Yeah. If, when you work on the given data, if the data is not organized, you may need to spend more time to do the processing. Okay? Yeah. But if you can organize your data in some way, in some special way, then you can improve the overall performance. Yeah. So that's some, common practice people use. Yeah. All right. Yeah. So here we want to take advantage of the structure for better performance. Okay. Yeah. To understand this point, yeah, we need to use many examples later. Yeah. All right. Yeah. So here, so for this simple example, yeah. First, we already have a solution. Yeah. You just compare element one by one with the given key until you go through all the elements in this array, right? That's the solution. Yeah. All right. So here we just do some analysis. Yeah. All right. The basic operation we use here, comparison. You do not need to do addition, multiplication. You only need to do comparison. Okay? Yeah. So what kind of comparison? Compare K with the current element in the array, A of I. Yeah. When you start, you set initial index value, I equals 0. Yeah. Then you do iterations. If K equals A of I, you can return the value of I. When K not equal to A of I, you need to do more comparisons. Yeah. All right. So that's the, solution. Yeah. So here, iteration, you need to do further iterations. Yeah. Do another round comparison. Okay. And so on until you reach the end. Yeah. The end, this is the end point. Yeah. If after you do the comparison with the last element, still you cannot get a hit. Yeah. No element equals the given key K, you just return -1 for your function. Okay? Yeah. So that's the whole solution. Yeah. But here we want to do discussion on the efficiency analysis. Yeah. Our main focus here is for efficiency analysis. Yeah. Okay. Yeah. Yeah. Here, the algorithms, there is a name for it. We call it sequential search. You apply comparison sequentially, sequential search, or linear search. Yeah. Linear search, so that focus is on, efficiency. Now, efficiency is a linear function. Okay, yeah. So that's the linear search. Yeah. Sequential search, so we do comparisons in a sequential way. Yeah. All right. Now, efficiency analysis, a little bit. Yeah. to do here, let us count the number of comparisons for the stable measure for the efficiency. Okay, yeah. So let us do the chart here. Yeah. Let us consider all the possible cases for the comparisons. Yeah. All right. Here, look at the given key. Key equals one of the elements in the given array, and the last case, no match. Yeah. So we consider those n plus 1 cases. The total, there are n plus 1 cases. Okay, yeah. For each case, let us look at the number of operations. Yeah, all right. If k equals the first element, we just need one comparison. That's it. Okay, yeah. So we return the result by one comparison. Okay, yeah, that's the smallest comparison number. Yeah, if k equals a of 1, 2 comparisons, and so on. Okay, yeah, until the last element k equals the last one, n comparisons. Yeah. Then no match. If no match, you need to compare all the elements. For the no match case, that's also n comparisons. Okay, yeah. After that, now we can do, we can do some summary. Okay, yeah. Let's look at all the cases for some discussion here. Okay, yeah. First, we notice that case 1, that is the best case because the number is the smallest. The best for us. Okay, yeah. Just the one comparison, we can find a solution. That's the best we can have. So we call it the best case. Okay, yeah. Then the last 2 cases, that comparison number equals n, the worst case. Okay, yeah. So that's the worst. Yeah. So the best case and the worst case. Yeah. That's very straightforward. Yeah. But there is another important view. Yeah. We want to see what is the overall efficiency. We want to measure the overall efficiency. Yeah. Definitely, best case, it's a not good way to evaluate, to measure the overall efficiency. Right? The best case, you cannot use best case 1 for the overall efficiency. Worst case, not good number, you cannot use the worst case number n to measure the overall efficiency, right? Yeah. So here you need to use a new way for overall efficiency. That's the average case. That's the concept we need to, put a lot of emphasis here. The average case efficiency, that concept. Now, I want to do some discussion here. The measure should include all the cases. The best case, you only use one of the cases. Worst case, you also use one of the cases. But here you need to consider all the cases, not just one case. Yeah. So that should be the average case efficiency. Yeah. Yeah. But if we want to consider all the cases for this particular question, we need to make some assumption. Yeah. Otherwise, the answer could vary, quite different. Yeah. So we need to make a little more assumption to provide better description of the answer. Yeah. So let's see. So what is the assumption we need to make? Yeah. Now, the C.2 topic, average efficiency. This topic. Yeah. All right. Still, yeah, in this problem, let's make this assumption. Assume that these cases have the same probability. That's reasonable. The first n cases, they have the same probability. Okay, case 1, case 2, through case n, they should have equal probability number. Okay, yeah, that's a reasonable assumption. Yeah, but regarding the last case, no match case, then we need another assumption. Okay, yeah. The index case, yeah, what's the index case? The function returns a valid index value. Yeah, here we mean the function returns a valid index value. Okay, and that means 0 through n minus 1. Yeah. And the minus 1 case, this is not a valid index, right? Minus 1. Yeah. So that's the no match case. Yeah. So we consider these two cases and their probability. Yeah. The index case, let us assume the probability is P. Yeah. P is a number between 0 and 1. The probability, valid probability number in this range. Yeah. Then the negative case, 1 minus P. Yeah. So that's the, simple probability property. Okay. Yeah. And this P, you can see this P can change for different problems. The P could be different. Yeah. Yeah. But in the real world, you may ask, how do we get this P in the real world applications, right? Yeah. So in the real world, to get this P, we can do by experiments. Right? Yeah. Because real world, when you do the search on a particular group of data, yeah, so you have all the data, you can do statistics on all data, so you can find some probability number. Okay, yeah. All right. So with this number now, we want to find the formula for the average case efficiency. Yeah. So let's look at that formula. Yeah. All right. So under the reasonable assumption, yeah, let's do some average case efficiency measure. All right. Yeah. Here, when we look at the average case, we consider two subcases. Now, so here, these two, yeah, two subcases. Okay, yeah. For the first subcase and the second subcase, now, we want to see in the first subcase, what is the average efficiency number? All right, yeah, because that will be much easier, yeah. And if we just take the ordinary average for the first subcase, yeah. 1 plus 2, the number of comparisons for all n cases, then we take the division because there are n cases in that subcase, yeah, n cases in that subcase. So we do division by n, and after simplification, we get this number. Okay, that's the first subcase. For the second subcase, there is only one case, right? The no match, only one possibility, one case. Yeah. So we do not need to take the average, or the average is the same number, n. So now we have these two average efficiency numbers for two subcases. But we need to combine these two subcases in certain way, in an appropriate way. Yeah. Here the question, what is that appropriate way? Okay. Yeah. That is important. Yeah. How to make appropriate? Okay. When we combine these two subcases, what is the appropriate way? Yeah. All right. So here we need to use the probability numbers. These two probability numbers. Yeah. All right. So let's look at the combination of these two subcases. Yeah. All right. Yeah. So here for the first subcase, the probability equals P. The second subcase, probability equals 1 minus P. Now, how do we understand these two probability numbers? Okay, yeah. The probability, can we see the larger the probability, the more contribution of that subcase? The smaller the probability for each subcase, the smaller that corresponding subcase for the contribution. Yeah. So that's the simple observation. Yeah. Then when we put them together, we need to factor in their appropriate contribution percentage. Okay, we need to factor in that. Yeah. Here, that observation tells us we should do weighted average. The appropriate, what's the appropriate average? The appropriate means we should do weighted average. Weighted average, this type of average. Yeah. So what's the weighted average? We need to associate with different weights. When we combine these two average numbers, we need to associate these two numbers with appropriate weights. They are appropriate weights. These two numbers. We treat these two probability numbers as two weights when we do weighted average. Okay? All right. Yeah. Here, the answer, the final answer, the weighted average, the first number, we need to multiply its corresponding weight, that's P, probability. For the second efficiency number, we need to multiply its corresponding weight number, 1 minus P. So the final answer is this expression. Yeah. Here in this question, you can see I spent a lot of time. I try to let you understand how to find average case efficiency. What is the correct way to find average case efficiency? Here you can see you need to do a lot of work. Not like best case efficiency, worst case efficiency. Usually that's easy to find the best case efficiency, worst case efficiency. But to find average case efficiency, you need to do a lot of work in the right way. Because later, you have many chances you need to calculate weighted average for the average case efficiency. Okay, that's non-trivial. All right, yeah. Here, this is the first time we calculate overall efficiency. Yeah. That corresponds to the average case efficiency by weighted average. Yeah. All right. Yeah. Here for this formula, yeah. So if we want to really see its efficiency number, yeah, a good way is to look at its dominant term. Yeah. Last time in Part B, I mentioned that dominant term a little bit, right? I used that word, dominates. Yeah. Quadratic polynomial dominates linear polynomial. Yeah. Here, yeah. And I remember Sarah mentioned that leading term, right? Yeah, leading term. Yeah. Here, can we look at that leading term again? Yeah. We call it dominant term. We know the leading term is the dominant term. Yeah. Here, leading term, the term corresponding to n times p, and also 1/2. Yeah. And here, n times this number. Yeah. You need to put them together. That plus 1 can be ignored. So the leading term is big parenthesis 1 minus 1/2 p times n. That's the leading term. Okay, yeah. And we know from this leading term, we can see it's a linear function. Yeah. That's why we call this search algorithm linear search. Okay, yeah. All right, so we complete this topic, our computing problem number 2 here. Yeah, because it's a very simple problem. Yeah. But we have some important concept we can learn in this topic. Yeah. All right. Next, yeah, we run out of time, but the next topic I like to prepare you for the programming project. Yeah. So this topic is for our programming project number 1. Yeah. And our first programming project will be given in week number 3. That is the next week. Yeah. This week is the week number 2, right? So, and based on our timeline schedule, it will be given in week number 3. Yeah. And because today we do not have time, so let me delay this topic to later or to week number 3. Yeah. Just our scheduled time for project discussion. Okay. Yeah. All right. So let me stop right here.